Welcome to my talk. So my name is Omer. I'm the CEO of Ingonyama. Basically what we do at the company is we're in charge of the hardware infrastructure to improve performance of zero-knowledge computation, mostly provers. What it means, in part, is that we take or we look at or try to identify math primitives that can become bottleneck in certain ZK computations, and then we figure out a way to accelerate those. A couple of popular examples are the MSM, the multiscalar multiplication, and the NTT. So these are like the known ones. And in this short talk, I would like to present kind of a new one, a variant, you'll see. So starting with the basics with the MSM and NTT. So MSM, I'd like to look at it as kind of like a dot product between a vector of scalars and a vector of EC points. And we have the main algorithm that usually is being implemented is the Pippinger or the buckets algorithm. And in hardware, we have certain ideas on how to do that. We have one paper, there are other papers, of course. Now with NTT, things are a bit different. So this is like only field operations, as you can see. There's this loop basically that needs to repeat n times. The most popular algorithm to solve the NTT is the Cooley-Tukey FFT. And here again, when it comes to hardware, there are different ways to implement. We have one direction, there are obviously other directions. I want to focus now on the NTT and try to represent it in a different way, okay? So take this representation, which is in a matrix form, okay? So it's basically the same, just open it up. Now we have a vector of scalar or field elements multiplied by this matrix of twiddle factors, basically constants, right? Doesn't really matter. So now I want to introduce the ECNTT, which is very simply put, instead of vector of scalars, we have vector of elliptic curve points, yeah, or group elements. Same thing. And this is, I mean, if you look at it as a polynomial, so this is like a polynomial where the coefficients are elliptic curve points, okay? So let's now add it to our table. And basically, the software algorithm is the same, okay? So it's linear. It would work just the same if we do so it's the same Cooley-Tukey FFT. But what I want to claim first is that in hardware, this is less trivial. So I cannot just say, okay, same thing that worked for NTT in hardware now going to work for ECNTT. Why do I say that? Okay, so first, you know, in terms of memory, right? So an EC point can be represented as 2 or 3 field elements. So basically, it's like 2-3 times larger in memory. But what's most important is that the basic operation being done in an NTT is the modular multiplication. While in ECNTT, the basic or what consumes most of the computation is an elliptic curve addition. Okay, now this is a big difference because modular multiplication, we can do it very efficiently in hardware. So today in NTT implementations in hardware, the bottleneck is mostly in the data transfer or in the access to memory. While once we introduce this ECNTT and move into elliptic curve addition, then computation become much more dominant, right? Like each EC addition operation can be like 10x or even more, or like order of magnitude more than modular multiplication in complexity, many more clock cycles. So it kind of shifts the focus. Another thing is that we can do a very deterministic computation when it comes to modular multiplication, which is not the same thing with EC addition, right? It depends on different factors, and basically we need to work in kind of like an amortized time, okay? So let's keep it as an open question on how this can be done in hardware. What I want to now go and try and do and try to convince you that this is actually important, primitive as a standalone, right? So my first example is from Aleo. This is a blockchain with privacy-preserving applications, and they baked in basically a zero-knowledge prover inside of their consensus in a way, right? To put it in simple words. As you can see here, they launched recently an incentivized testnet, and our prover basically got to 50% of the network. So one way that we've managed to do that is the following. So this is basically the algorithm, what Aleo wanted hardware to accelerate, and when you run it very fast or with high throughput, you are able to get more credits or more tokens from the network. And without going into the numbers, like I wouldn't have time to actually go step by step, but basically we have like a setup or a pre-processing phase and an online or runtime phase. And you can see that the main operations here are the usual NTT and MSM. So one thing that can be done that we noticed is that we can actually extend or add some operations to move some things to the pre-processing phase, and then we are left only with a smaller size MSM in the online phase, right? So basically, if I want to summarize, we take a computation that was supposed to be bottlenecked by 2n size MSM and 2n size NTT, and we replace it with only half size MSM in the cost of just doing a pre-computed ECNTT, okay? So you can think, I mean, there are several different reasons why this is way better when it comes to actually building an accelerator, right? You know, just one primitive, no need to go in and out or something like this. And it makes it much more easy to basically have everything inside of the hardware. However, you can say something like, this is pre-computed. I don't really need to accelerate ECNTT. Okay, so this is maybe one kind of motivation, but let me give you another type of example where I actually need to run ECNTT in runtime significantly. So here I want to go to Danksharding. And in Danksharding, for those of you who don't know, there's this role of a builder. So this is the one basically, or it's part of data availability sampling. This is the one that needs to do some hard work. Obviously, it will be incentivized in some way, but basically the hard work or part of it is to sample some field elements and then to provide some KZG evaluation proof that all of these field elements are correct, okay? So again, I don't have time to actually explain how this is work, but this is something that happens quite often in Danksharding. And here we have the Face-Kovatovich trick that it's basically just like solving this like really, really nice, which basically says that, and here I'm using instead of L, I'm moving to index N. So if I have a polynomial with n evaluations and I want to compute n KZG proofs, the roots of unity, right? So this is exactly what I can actually use this trick for. So usually you can think about it as, you know, like you have few MSMs that needs to be computed at the same time. So like n times n size MSM. So it's O of n square. But using the fact trick, I can actually do the same in O of n log n. Okay? And in the process, I do need to use ECNTTs. Okay? So here I was too lazy to actually write down like the entire protocol, but this is taken from the latest update to the paper by FK. And again, there's some pre-processing step, but I just want to point out that there are at least two steps, and I actually think there are three, where you need to do this ECNTT. Now remember that in software, and there's a reference implementation, it goes really, really smooth. It's just the same algorithm, just replace the scalars with elliptic curve points, but in hardware it's going to be much more interesting, I suppose. Okay? Finally, there are other applications. So the latest lookup table paper, the CQ paper, is basically the cached quotient side. This is CQ, stands for CQ. This is actually computed using the same trick and therefore employing ECNTT. Although I have to say this is, again, done as a pre-processing step. So next steps. So first I want to kind of, I think it's a good introduction to just, you know, this is an ECNTT. Now that we are familiar, let's see where we can use it. I think that the Aleo guys, where they have this like design in mind, basically to take, you know, entity, MSM, vector multiplication, all of the steps that like you want hardware to accelerate, and you could have changed it into something which is just like small size MSM. Probably we're not aware of ECNTT and how this can be used. Maybe there are other places where this can be utilized correctly and be applied. And I think that, and at least what excites us the most, is to implement it in hardware. So soon we're going to release an open source library that is based on GPU, a GPU library. Part of what it will implement will be this ECNTT, and of course we'll invite everyone to collaborate, use it, and impact the roadmap. That's it. Yeah.
Do you have an idea of the degree from which it became interesting to use it in CNTT instead of Pinger? Because I guess it's like when you choose for in the modular field, you use Karatsuba or A50, or you have some kind of trade-off where there is a degree where the method.
Yeah. So the question is kind of like, when is it becoming interesting? And just to Yeah, just to explain, you know, in ZK, usually we are dealing with like these huge vectors, and you know, therefore, like entities of such huge vectors, like obviously require hardware, and it's not necessarily the case here. So for example, I left in Danksharding the parameter L, and L might be small, right? And therefore, we might don't even need to do it in specialized hardware. So that's kind of an open question. So I don't really know what's the kind of the critical mass when it's going to become interesting. I can definitely tell you that there is usage. Like Aleo is a real-world usage where you can, I mean, we didn't do the ECNTT in hardware, but I mean, at least it was useful. So even if not for the hardware sake, just like for getting to know this primitive as its own. More questions?
Maybe a broader question. So you guys have worked with Aleo probably. I know you've like contributed to huge acceleration. If you can talk more about like what the experience was like and the benefits from really seeing like hardware acceleration for that actual their testnet.
So as a hardware company, you usually don't just build, because you know, we can build hardware size of a soccer field, right? So usually you have some constraints like area, cost, and also something you want to optimize for. In the case of Aleo, the goal was throughput. Basically, you want to fit in as many proofs as possible per unit of time. In our case, I mean, we took it as kind of an exercise. It was an interesting to analyze the algorithm and then implement it end-to-end in a GPU. I don't know. I mean, it's just like any other mining operation. You know, we've been working with miners, data centers, retail, basically everyone. Mining pools just utilize their GPU. At some point, by the way, once you go all in, like full GPU, you don't need the CPU. Therefore, you can actually run it on old Ethereum miners, for example. So at some point, it just like became like everybody just were using their GPUs. It was very fun to observe. Yeah.
I understood it makes ECNTT makes most things faster, especially in proving. I didn't understand what it does actually. Like when is it used? I understand it's for ZK proving, but at what point of the proof?
Right. So recall the first slide where I tried to make it like very abstract. One approach in order to accelerate ZK proof is to identify bottlenecks, and then every time they are called as part of the protocol, you just like move it to the hardware. I mean, this is like a very simplified approach. And what's interesting about this ECNTT is that at least in like existing ZK proofs, you don't see it right now. I mean, it's not a tool that we are using, and it's mostly something that at least we noticed once you start to put more things into the hardware, and then you see there are shortcuts. Maybe if I can use this stuff, then I can move some stuff to pre-computation, or I don't know, if I need to batch many commitments or many kind of KZG commitments, then this can be deployed. But this is another kind of good question. Once we know that this like element, I mean, how can we use it? CQ, I think, done like a very, if you look at the CQ paper, right, by Ariel Gabizon et al., so you see they provide a very significant part of the paper to discuss how they are utilizing this thing. But they are using it like at a higher level. They are using it at the like the factory, right? So it's already in the, they already assume that this is like being done by this like on-off and login, right? But, yeah. Okay, thank you.